Welcome back. Today we're looking at section 7.3 on trig equations. So they start us just with asking, hey, does this work? So is theta equals pi over 2 a solution to sine theta plus 1 equals 2? Well, little substitution, sine of pi over 2 plus 1 possibly equal to 2. The little question mark there is because we haven't established that it is equal. We are seeking to find that out. Sine of pi over 2, though, is 1. 1 plus 1 possibly equal to 2. 2 equals 2. That's true, so yes. If we consider the same one is then theta equals 5 pi over 2, a solution. So same previous one. So sine of 5 pi over 2 plus 1 possibly equal to 2. Well, 5 pi over 2, notice that is pi over 2 plus 2 pi. Plus 1 possibly equal to 2. And since we're of the form sine of theta plus 2k pi, that's the same as sine of pi over 2 plus 1 possibly equal to 2. And we saw that that one ended up as true. 1 plus 1 equals 2. 2 equals 2. So a yes on that one as well. So the pi over 2 was not a unique solution. 9 pi over 2 would work as well. It would be pi over 2 plus 4 pi. So since the solution is not unique over the set of real numbers, we can write sort of a general form for angles that will work for this. We can say that, okay, well, as long as we have something that looks like theta plus pi over 2 plus 2k pi, k is in z, the set of integers. Zahlen is the German word for number, if you're wondering why they use z for integers instead of I for integers. And the mathematician that created the notation was German, so that was what he picked. Notice the 2 and pi is one full revolution. So if we just keep spinning around, we would keep hitting the same point again and again. So we have multiple points that would work for this. So on these equations, the domain becomes a little bit more important. Are we talking negative infinity to infinity, or are we talking, as this next one, theta is in 0 inclusive, 2 pi exclusive? So in other words, one full lap around the circle. We'll do cosine of theta is root 2 over 2. We can sketch our unit circle for that. So root 2 over 2, one place we know that's happening is at pi over 2, since we have root 2 over 2, root 2 over 2 happening at pi over 4. They're asking about the cosine, so over here the root 2 over 2 would be the same for the x coordinate. So that would be at theta equals pi over 4. Theta could also equal 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4. So we have two solutions on that interval. After that, we've hit the 2 pi limit on that one again. So that one had just 2 solutions. Well, if we lifted the domain restriction on the previous problem, so if we had the equation cosine theta is equal to root 2 over 2, and this time just said theta is in the set of reals, well, we know that we have theta equals pi over 4, but then we could have any number of laps around the circle that still land us on the same spot on the unit circle. So pi over 4 and spin around 2 pi beyond that, 4 pi beyond that, 12 pi beyond that, any even number of pi's beyond that. So there's our plus 2k pi. We could also spin backwards. If I spin 360 degrees in the negative direction, I'm still landing back where I started, so we can have a plus or minus 2k pi for that. It depends on how we want to define k. If we want k to be in set of whole numbers, we can define it that way. If we want k to be in the set of integers, then we have the plus or minus covered by the fact that the integers have both positives and negatives. Now remember, we also excuse me, we also had the 7 pi over 4, and with that one also we can spin around any number of full rotations. So k is still in Zelen Z. So then our solution set, little bit messier looking, but it covers many more solutions. All right, so our next one, we're going to look at what's considered to be a linear trig equation. So in this one, theta is going to be on 0 to 2 pi. So we'll just do first full lap around. Our equation, negative 2 cosine of theta minus root 3 is equal to 0. So this is kind of equivalent to back in our just plain algebra days, negative 2x minus root 3 is 0. So we would add root 3 to both sides, negative 2 cosine theta is root 3, divide both sides by negative 2, so cosine theta is negative root 3 over 2. Well, on our unit circle, we've got a couple places that fit that bill. So our cosine is at a negative root 3 over 2, so that is 30 degrees above or below pi. So we have negative root 3 over 2, 1/2, negative root 3 over 2, negative 1/2. Both of those have a cosine value of negative root 3 over 2. So then that would be pi minus pi over 6. So 6 pi over 6 minus pi over 6, 5 pi over 6. Or pi plus pi over 6, so 7 pi over 6. We don't need the plus 2k pi because they restricted the domain for us on this one. So 2 spots where that can happen. 30 degrees above and below 180. Alright, so this next one we start messing around with our argument of the cosine. So they're just, on these they're going to be asking us to solve, would be the direction, of course. If they give us an equation, they want us to solve it. So cosine of 2 theta is negative 1/2. theta is on the interval from 0 to 2 pi, inclusive on 0, exclusive on the 2 pi. One note with this, since we have 2 theta in here, we can really make 2 full laps around. If I go to the sort of endpoint that I'm allowed to get close to, think the idea of limits, 2 by 2 pi would be 4 pi. We can get close to 4 pi. We can get close to 2 full cycles for this. So first we look at where this would happen. So we're looking for a negative 1/2. For our cosine. So negative 1/2 root 3 over 2. So one spot that it happens, negative 1/2, negative root 3 over 2 is another place where that happens. So those are each 30 degrees off of the vertical axis. So we have pi over 2 plus pi over 6. So that would be 4 pi over 6, which then gets us to 2 pi over 3. The other one is 3 pi over 2 minus pi over 6. So 9 pi over 6 minus pi over 6, 8 pi over 6, which is 4 pi over 3. So we know the 2 spots that this would happen. Now we put it to work for us, though. So we're going to continue this one on the next page. So that was if we just had theta, though. But we really have 2 theta. 2 theta is equal to 2 pi over 3. We can do the general plus 2k pi. Or 2 theta is worth 4 pi over 3 plus 2k pi. So each of these we can divide by 2 to get the theta by itself. So theta is pi over 3 plus k pi, or theta is 2 pi over 3 plus k pi. And we can, of course, here k is in the set of integers. K is in Z. So at that point, we just see what fits on the interval that we were given. We were told that, recall from the previous page, I'll just kind of toss it up here. We had it on the previous page, theta had to be in 0 to 2 pi. So if k equals 0, theta equals pi over 3, that's on this interval, or theta equals 2 pi over 3, also on that interval. If k equals, we'll see if we can go backwards. Sometimes you can, sometimes you can't. K equals negative 1. Theta is pi over 3 minus pi is 3 pi over 3, negative 2 pi over 3. That's not on our domain, so we don't want that for the pi over 3. Testing it out with the other guy, we run into the same problem. Theta equals 2 pi over 3 minus 3 pi over 3, negative pi over 3. We don't get to keep that guy either. So we then try, well, what happens with positive 1? Theta equals pi over 3 plus 3 pi over 3, 4 pi over 3. Sure, that's before 2 pi. We get to keep that. I'll put little check marks by the one we get to keep. Not official mathematical notation, just something I find handy sometimes. 2 pi over 3 plus pi, 1 pi would be 3 pi over 3, 5 pi over 3. Sure. That's before the 2 pi limit. We'll keep it. If we try out k equals 2, theta equals pi over 3 plus 2 pi is 6 pi over 3, 7 pi over 3, no dice there. And of course, if we add more to that, more to something bigger, we're still bigger. So we had 4 elements in our solution set. So we can express this as a solution set. We could keep pi over 3. We could keep 2 pi over 3. We could keep 4 pi over 3. And we could keep 5 pi over 3. So 4 elements in our solution set. We'll do a little bit with calculator approximations. I generally am looking for exact values unless I specify we want an approximation. We'll to the nearest hundredth. So we'll go tan theta is -5. And theta in 0 to 2 pi. So, of course, we'll take the arctangent of both sides. So theta is the arctangent of -5. And again, they wanted a decimal approximation. I'll try to keep this roughly at an angle that you can see the screen fairly well without glare or shadow. Not always a super easy feat. So arctangent, second and above tangent, and we're asking about -5. Close it in, and my apologies, I'm in the wrong mode. We want radians. We'll go back to the original second quit. All right, so there we are. There is our number of radians. So we get theta is approximately, we get -1.37. Again, that's rounded to the nearest hundredth. So one thing you might notice, and we'll store this as our x. So store is above your on-off key, and we'll hit that as x. So just remember that's our x. One thing you might notice right away, that is not on our interval. So if our tangent is -5, if I'd like -5 to look like a fraction, we're always allowed to divide by 1. So on this one still, even with the calculator, we're doing a little bit of work with making a sketch of the unit circle. I think that's the closest I've ever drawn to something reasonably resembling a unit circle freehand. Pretty excited about that. So tangent is y over x. So it's either -5 over +1 or +5 over -1. Both of those would return a -5. So if this angle is my -1.37 radians, I can find this angle to sort of complement that idea, bring me back to the same spot. So I'm going to do 2 pi and then I'll do our x. So I'll make sort of a lap around, and I get approximately 4.909 blah 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 blah. But the fact that I have a 9 next door, 4.909, and we're rounding to the hundredths, 4.91. So theta approximately 4.91. That is in our 0 to 2 pi, 2 pi 6.28318 blah 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 blah. So then we'll look at this other guy. Well, this one we can try pi plus. So pi plus our x value. This one we get 1.768, so theta approximately 1.77. That is also on our 0 to 2 pi interval, so we get to keep both of those. So next we'll look at some trig equations that are in quadratic form. Do 2 cosine squared theta minus cosine theta minus 1 equals 0, and we'll restrict theta to being on 0 to 2 pi again. Hopefully you recognize inclusive on the 0, exclusive on the 2 pi. Hopefully you recognize the form here. We have a square of first power, no more cosines, equals 0. We can do a little u substitution. Let u equal cosine theta. You just put in a mannequin, put in a dummy variable. 2u squared minus u minus 1 equals 0. So there's our little crash test subject there. Well, this one, oh, weren't they nice to us? They gave us something that happens to be factorable over the integers. 2u plus 1 by u minus 1 equals 0. So u is negative 1/2, or u equals 1. This time I actually just wrote out or instead of using the union symbol. With my handwriting, the union symbol and the letter U don't look terribly different. So then we back substitute. We put the real deal back in. We're done with our placeholder, our little mannequin there. We can put the real one back in. So cosine theta is negative 1/2, or cosine theta is a 1. What we're looking for, where those happen on our dear friend the unit circle. So cosine is negative 1/2 here and here, so negative 1/2 root 3 over 2, and negative 1/2 negative root 3 over 2, and cosine theta equals 1 right there. So we have 30 degrees past pi over 2 and 30 degrees before the 3 pi over 2. You'll recall, hopefully, from the previous page that those were 2 pi over 3. 4 pi over 3. And we have one more at theta equals 0. Or you can, if you don't like the union notation, you can just do a solution set. So 2 pi over 3, 4 pi over 3, 0. And our domain was restricted one lap around, so that's why we didn't throw the 2 pi in. It was excluded from our domain, and that's why we don't have any plus 2k pi's involved. So the next thing they have us practice with in this section is solving using identities. So a little bit of practice with that. The more you remember those, the easier your calc days are going to be. So we have cosine squared minus sine squared plus sine theta equals 0. Well, I notice here that my sine by itself, my first power is written in terms of sine. I've got a sine squared here. Let's try to rewrite this guy in terms of sine as well then. Well, recalling that cosine squared theta plus sine squared theta equals 1, I can swap that cosine squared theta out with 1 minus sine squared theta. So that is just this much of it. I'll bring the rest along. So minus another sine squared theta plus sine theta equals 0. We can do a little bit of rearranging of that and say that this is 1 plus sine theta minus 2 sine squared theta equals 0. And that looks like one of our quadratics. So we'll do another u substitution. Let u equal sine theta. 1 plus u minus 2u squared equals 0. Factor that guy over the integers. So 1 minus u by 1 plus 2u equals 0. So u equals 1, or u equals, that would be -1/2. Put our real deal back in, so sine theta is 1, or sine theta is -1/2. And then we just make our little sketch of the unit circle. So sine theta equals 1, that's happening at pi over 2. Sine theta is -1/2. So that is down here or down here. So either at √3 over 2 -1/2, or at -√3 over 2 -1/2. So each of these is 30 degrees off of the horizontal. On this one, did they give us restrictions? This one, I believe they wanted us to do in, yeah, we'll do 0 to 2 pi, and that's my apologies. I forgot to mention where theta is. We'll keep this on 0 to 2 pi. Alright, so 30 degrees past pi, so 6 pi over 6 plus 1 pi over 6, 7 pi over 6. Pi over 2 for this guy. So 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6. So you can either do the OR notation or the solution set. So pi over 2, 7 pi over 6, 11 pi over 6. Alright, so our next at-bat, we'll try cosecant squared theta is cotangent of theta plus 1. We'll solve this one the same as last one on 0 to 2 pi. This time I'll remember to tell you that at the start of the problem though. Okay, so on this one, cosecant squared theta minus cotangent squared theta is worth 1. That was one of our other identities. If you need to convince yourself of that, turn those guys into sines and cosines, and you should be convinced. So our cosecant squared, we can replace that with 1 plus cotangent squared of theta, of course, equals cotangent theta plus 1. The plus 1's drop, so we'll get this. This is looking sort of quadratic in nature. Cotangent squared theta minus cotangent theta equals 0. U equals cotangent theta. U squared minus U equals 0. U by U minus 1 equals 0. U equals 0 or U equals 1. Toss the original guy back in there. Cotangent theta equals 0 or cotangent theta equals 1. So cotangent, recall that is x over y. Also cosine over sine. So if cosine theta over sine theta equals 0, that means cosine theta had to have been 0. Places where the cosine is 0. Cosine is 0 at pi over 2. Also 0 at 3 pi over 2. Cotangent theta equals 1. Again, recalling that cotangent theta is the same as cosine theta over sine theta. If they're equal to 1, that means they're equal to each other. Cosine theta equals sine theta. Places where they're the same. Our unit circle. Root 2 over 2. Root 2 over 2. That's happening at pi over 4. That's also happening down here in Q3 when we have negative root 2 over 2, negative root 2 over 2. So 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. Or again, if you like the solution set, pi over 2, 3 pi over 2, pi over 4, 5 pi over 4. So then the last thing they have us try in this section, 7.3 is a bit bigger of a section, as you can see, approximating with the graphing utility. That's just using the point of intersection, and you've had plenty of practice with that in college algebra. We won't spend tons of time with it. 7 sine of x minus 3x is equal to 2. If we do y1 is equal to 7 sine of x minus 3x and y2 equals 2, we just find where they meet. Again, I'll try to find this sort of sweet spot where we have enough light to see it and not a huge amount of glare. So y1, 7 sine of x, close it on up, minus 3x. y2 is 2. And we'll start on zoom 6, the standard window. And my apologies, let me turn that stat plot off. That was something for my Calc 2 people. Back to our picture. So there's our sine curve, there's our line. and it looks like it meets in 3 spots. So second and calculate, and we want where they intersect. That's option number 5. First curve will default to y1, second curve will default to y2, and I guess you just get close to where they meet, hit enter, it'll think for a minute, and round the x value to the nearest hundredth. We're not interested in the y value for 2 reasons. One of our equations is y equals 2, but another reason is if you look at the original equation, there were no y's in there. We artificially put them where we didn't really have any before. So we're only interested in the x approximations here. So negative 341, so negative 2.34. Do the same thing on the next two. So second and calculate, where they intersect. First curve y1, second curve y2, and a guess. It'll think for a minute after we get it close. X is then approximately 0.547. We call it 55. So we round, not truncate. And then one more. So second and calculate, point of intersection, first curve y1, second curve y2, and guess, arrow over until your cursor is relatively close. Hit enter. It'll think for a second, and our final x is approximately 1.657, makes us call it 1.66. If you want the set instead of the union, negative 2.34, 0.55, 1.66 would be our solution set. All right, so in 7.3, you're going to try out 13 to 93, the odds, and I'll find a rough equivalent in our my math lab as well for those of you that are doing that option. All right, if you have any questions, please get in touch. Otherwise, I will see you next time.